Have you ever thought about a power source that just keeps on going? I'm not talking about for a day or a week, but for decades, maybe even centuries? Well, today, we're diving into the incredible science of what you might call the forever battery.
We've all been there, right? That sinking feeling when your phone hits 1%. Our entire modern lives run on chemical batteries that, by their very nature, have an expiration date. But just imagine for a second if that limit just wasn't there. What could we do with a power source that could outlive the very device it's powering and maybe even outlive us?
Okay, so here's our game plan. We're going to start big with the classic 50-year battery that's been powering missions into deep space. Then we're going to shrink things way, way down to the micro world, where this tech is sparking a whole new revolution. We'll even take a look at how hobbyists are building their own atomic power sources at home. And to top it all off, we'll journey to the absolute cutting edge, a place where science fiction is becoming fact, the nuclear laser frontier. To really get a handle on the forever battery, we have to start where it's already proven itself in the most extreme environment imaginable: the silent, unforgiving vacuum of deep space.
I mean, just think about this. The Voyager probes were launched way back in 1977, and they are still sending data back from beyond the edges of our solar system. That is an absolutely legendary run for any piece of tech, and it's all thanks to their one-of-a-kind power source. Even now, as their power finally starts to fade, a mission that has lasted nearly half a century is just a phenomenal achievement for a battery.
So, how did they do it? The secret is something called a radioisotope thermoelectric generator, or RTG for short. And the principle behind it is actually beautifully simple. You take a chunk of radioactive material that naturally gets hot as it decays, and then you use that heat to generate electricity. No moving parts, nothing to break down, just steady, reliable power for decades.
And this isn't some brand new, futuristic concept. The idea actually goes all the way back to 1913. By the time the space age kicked off in the 50s and 60s, these batteries were already being used to power satellites. And of course, the technology hit its most legendary peak with the Voyager missions. So here's the absolute key difference. A chemical battery, like the one in your phone or your laptop, it's based on a chemical reaction that has a definite end. Once the chemicals are used up, that's it. It's done. But a nuclear battery taps into the slow, incredibly predictable process of atomic decay, which can trickle out energy for a ridiculously long time. All right, so we've been out in the grand scale of space exploration. Now, let's pull a complete 180 and zoom all the way in. Because the next great leap for this kind of power is happening at a scale you can't even see. Our world is now filled with these microscopic, smart devices called MEMS. We're talking about tiny little sensors and machines that need power sources that are just as small and, more importantly, just as reliable. Imagine a medical implant monitoring your health from inside your own body, or deep-sea sensors exploring the crushing darkness of the ocean floor. You can't exactly plug those into recharge. For these jobs, a battery that never dies isn't a luxury, it's an absolute necessity. Now, this is where things get really, really cool. Researchers are taking a whole new approach. Instead of just using the heat from radiation, these new microbatteries convert the radiation directly into light, which then gets turned into electricity. What you're seeing here is a breakthrough design where the radioactive atoms and the light-emitting material are basically fused together on a molecular level. Okay, let's walk through that. First, an atom of americium-243 decays and shoots out a high-energy alpha particle. Step 2, that particle immediately slams its energy into the surrounding terbium material. In response, that material lights up, emitting photons. And finally, a tiny photovoltaic cell. Think of it as a tiny solar panel, captures that light and turns it into electricity. It's this direct, intimate connection that makes the whole process incredibly efficient. But of course, there's a huge challenge here. The very thing that gives the battery its power, the radiation, can also be its undoing. So the holy grail is finding materials that can keep converting that radiation into light without just falling apart after years and years of constant bombardment. And that brings us right here into the Materials Science Lab. What you're looking at are samples of a transparent ceramic called GYJ-GAG. Scientists are, in essence, just blasting these materials with different kinds of radiation over and over to see what they can handle. They're trying to find that perfect recipe for a battery that truly lasts. And this graph,
This just perfectly illustrates the problem. Look at this. When the ceramic gets hit with beta particles, which are just electrons, its ability to produce light stays pretty strong, no problem. But when it gets hit with those heavy-duty alpha particles, the kinds used in that cool new design we just saw, well, its light output just plummets. That red line nosedives. The damage is severe. So this is the exact puzzle scientists need to solve, finding a material tough enough to stand up to alpha particles and just keep on shining.
Okay, so we've been in deep space and we've been deep inside a high-tech research lab. Now we're going to bring it all the way back down to Earth and into somebody's garage. It sounds like something straight out of a movie, but I promise you it's real. Using materials you can actually buy online, tinkerers and hobbyists are building their own working low-power nuclear batteries. Now, they're not powering a city, but they are absolutely proving the principle works.
This quote from a DIY builder, Samuel J. Burleson, just sums it up perfectly. What they do is take a small glass tube of tritium gas, that's a radioactive isotope of hydrogen that naturally glows, and they put it right next to a tiny solar cell. The tritium's glow is really faint, but it's constant, and it's enough to generate a tiny but continuous electric current. It's the exact same idea as the high-tech versions, just built with off-the-shelf parts.
Amazing.
Okay, for our final stop, we're going from something you can build at home to something that pushes the absolute boundaries of physics. This is where the whole idea of a forever battery becomes something else entirely.
See, all the technologies we've talked about so far are passive. They just sit there and collect the energy from an atom's natural, random decay. But what if you could control that process? What if you could actually tell the nucleus when to release its energy? Well, that's where the real future is headed.
This is where things get a little mind-bending. I know this diagram looks complex, but the basic idea is just astounding. Researchers are firing an incredibly precise and intense laser directly at the nucleus of a thorium-229 atom. They are literally pumping energy into the nucleus, kicking it up to a higher energy state, almost like charging it up. This gives them a way to store and maybe, just maybe, release that nuclear energy on command.
And if we can master this kind of control, the applications are just staggering. We're talking about the potential to create things like nuclear lasers, clocks so ridiculously precise they would completely redefine how we measure time, and totally new ways of storing and releasing energy that would be far, far more dense than any battery we can even dream of today. So just think about the incredible range we've just covered. We started with this huge generator powering a probe on a 50-year trip past Pluto. And we've ended up with a single laser tweaking the very core of a single atom. It's a journey from the edge of our solar system right into the heart of matter itself. It's a technology that's somehow both ancient and brand new, operating at the very largest and the very smallest scales we can imagine. So the real question isn't if we'll see atomic power show up in more places, it's where it will pop up next. What problem will the forever battery solve tomorrow?